Hello students, today we will be covering NCERT Exemplar questions from 13.2 to 13.8 of chapter Nuclei. This is the disclaimer. Let's start by looking at what you will be able to do by the end of this lecture. By the end of this lecture, you will understand how binding energy, decays, types, Q value and nuclear force apply in nuclear reactions, helping you grasp key concepts in atomic structure and energy release. Next, we will be continuing to discuss the application of radioactivity. There are a total of 26 NCERT exemplar questions in the chapter Nuclei. In this lecture, we will focus on 7 out of 26 NCERT exemplar questions in the chapter Nuclei, specifically questions 13.2 to 13.8. So, our first question in NCERT exemplar 13.2. The gravitational force between a hydrogen atom and another particle of mass m is calculated using Newton's law of gravitation. The formula is given as F equal to G capital M small m upon r square, where F is the gravitational force, G is the gravitational constant, m is the mass of hydrogen, and small m is the mass of other particle, r is the distance between the two particles. The task is to determine the correct expression for capital M, the mass of hydrogen atom, when calculating the gravitational force. So 4 options are given. So first option, capital M equal to small m proton plus m electron. This option assumes that mass of the hydrogen atom is simply the sum of masses of its proton and electrons. B option is capital M equal to m proton plus m electron minus B upon C square, where B equal to 13.6 electron volt. This option accounts for the binding energy B of electron in hydrogen atom. The term B upon C square represents the relativistic mass reduction due to binding energy. C option is m is not related to the mass of the hydrogen atom. D option is capital M equal to m proton plus m electron minus V mod upon C square. V mod is the magnitude of the potential energy of the electron in the hydrogen atom. This option uses the potential energy of electron as the measure of the binding energy. So correct option is B here. Let's discuss the solution in detail. Given the force F between two masses capital M and small m is equal to G capital M small m upon r square, where r is the distance in kilometers. Here capital M is the hydrogen atom's effective mass. Now capital M is calculated as sum of electrons and protons mass minus B upon C square, where B is the binding energy of hydrogen atom, which is equal to 13.6 electron volt. Binding energy is the energy equivalent to mass defect in hydrogen nucleus. Mass defect is the difference between the total mass of the separate nucleons and actual mass of the nucleus. Now let us see why other options are incorrect. The option A is wrong because it ignores the hydrogen atom's binding energy, that is the energy corresponding to mass defect, and tells us how strongly the nucleons are held together inside the nucleus. The hydrogen atom's mass m is slightly less than the sum of proton and electron masses due to binding energy. Option C is incorrect because the calculation for gravitational force requires the mass of the hydrogen atom, which is related to the masses of proton, electron and binding energy. And binding energy is essential to calculate actual mass of nucleus. Option D is incorrect because the term V upon C square represents the potential energy of the electron in the hydrogen atom, not the binding energy. The correct term is B upon C square, not V upon C square. Next exemplar 13.3. When a nucleus undergoes radioactive decay, it emits particles or energy which can affect the structure of the atom. However, the behavior of the electronic energy levels of atom depend on the type of decay. Radioactive decay involves the transformation of a nucleus, which can result in the emission of alpha particles, helium nuclei, and beta particles, that are electrons or positrons, or gamma rays, that are high energy photons. 4 options are given based on effect of radioactive decay on electronic charge levels of the atom. You have to choose the correct one. So options are: do not change for any type of radioactivity. B option is change for alpha and beta radioactivity but not for gamma radioactivity. C option is change for alpha radioactivity but not for others. And D option is change for beta radioactivity but not for others. So correct option is B here. Let's discuss the solution in detail. When a nucleus decays, it changes, affecting the atom's charge. A beta minus particle, that is electron, carries -1 charge. Alpha positive carries +2 and gamma has no charge. This alters the atom's electronic energy levels. When a nucleus decays, it affects the atom's electronic energy levels. Alpha decay involves the emission of a helium nucleus, that is 2 protons and 2 neutrons. This changes the atomic number and the number of electrons in the atom, leading to a change in the electronic configuration and thus the energy levels. Beta decay involves the conversion of a neutron into a proton or vice versa, which changes the atomic number but not the number of electrons. However, this can lead to a change in the electronic configuration due to altered atomic number. Gamma decay involves the emission of high energy photons without changing the number of protons or neutrons. Therefore, the atomic structure remains unchanged and the electronic energy levels are not affected. So, energy levels change in alpha and beta decay but not in gamma decay. Now, let us see why other options are incorrect. So, when a nucleus decays by emitting alpha or beta particle, it changes the atom's nuclear charge. For alpha and beta decay, this alters the electronic energy levels. Gamma decay doesn't affect charge, so energy level stays the same. So this option A is incorrect because the electronic energy levels do not change for alpha and beta radioactivity due to the change in the nuclear charge and the number of electrons in the atom. So option C is incorrect because beta radioactivity also changes the electronic energy levels, not just alpha radioactivity. Option D is incorrect because alpha radioactivity also changes the electronic energy levels, not just beta radioactivity. So next example 13.4. So in question, mx and my denote the atomic masses of parent and daughter nuclei respectively in radioactive decay. The question deals with the calculation of Q values for two types of beta decay, beta minus decay and beta plus decay. It asks which of the given options correctly represent the expression for the Q values in terms of the atomic masses of the parent and daughter nuclei and the mass of an electron me. The Q value represents the energy released during a nuclear reaction. The Q value determines whether a nuclear reaction is energetically favorable, that is Q is positive, or not, that is Q is negative. 4 options are given and you have to choose the correct one. So Q1 for A option, Q1 is mx minus my c square and Q2 equal to mx minus my minus 2me c square. Q1 equal to B option, Q1 equal to mx minus my c square and Q2 equal to mx minus my c square. C option, Q1 equal to mx minus my minus 2me c square and Q2 equal to mx minus my plus 2me c square. And D option is Q1 equal to mx minus my plus 2me c square and Q2 equal to mx minus my plus 2me c square. So correct option is A. Let's discuss the solution in detail. So in beta plus decay, nucleus of X with mass number A and atomic number Z converts into daughter nucleus Y with mass number A and atomic number Z minus 1 by emitting a positron and neutrino, and Q2 energy is released. So in beta positive decay, a nucleus emits a positron. The Q value is energy release calculated as Q2 equal to Mn and Zxa. So this is the Mn is the mass of nucleon of which atom? Which nuclei? Parent nucleus. Okay, so parent nucleus is X. So this is the mass of nucleons multiplied of parent nucleus X minus mass of all the nucleons of daughter nucleus, that is Z minus 1 Ya, minus mass of positron multiplied by C square. This shows energy comes from mass difference of parent and daughter nuclei minus the positron mass. Mn here is mass of nucleons and m is the mass of positron. After some modification, equation becomes Q2 equal to Mn, that is mass of nucleons of which nucleus? Zxa, X nucleus, minus plus Zme minus Mn, mass of nucleon of which nucleus? Daughter nuclei Y, minus Z minus 1 Me minus 2 Me c square. So we have modified this equation. Why? We are adding the mass of electrons to X nucleus and number of electrons Z minus 1 in daughter nuclei. So we are adding the mass of electrons also present in the atom. Now Q2 is equal to mass of parent atom. Now this is not mass of nucleons of parent nucleus. It is mass of atom because we have added the mass of electrons also. Okay, in the above equation, so we have multiplied Mn, that is mass of nucleons of X parent nucleus. We have added the mass of electrons Zme. Z is the atomic number of parent nucleus X. So if Z is atomic number, so number of protons in the parent nucleus is Z, and number of electrons in parent nucleus is also parent atom is also Z. So Z multiplied by mass of electron gives the mass of all electrons in the atom. So Mn, that is mass of nucleons of X atom plus the mass of electrons give us the mass of parent atom X minus mass of daughter atom Y minus 2Me multiplied by C square. Addition of mass of nucleons and mass of electrons in above step results in mass of entire atom. So now equation is Q2 equal to capital Mx minus capital My minus 2Me C square. This accounts for the mass difference between the parent and daughter nuclei minus twice the electron mass for positron. Okay, mass of positron and electron is same, multiplied by C squared. So in the question it is given that mass of parent atom is Mx and mass of daughter atom is My. Okay. So in beta minus decay, nucleus of X with mass number A and atomic number Z converts to daughter nucleus Y with mass number A and atomic number Z plus 1 by emitting an electron and antineutrino, and Q1 energy is released. So in beta minus decay, a nucleus emits an electron and an antineutrino releasing energy Q1. The equation is Q1 equal to Mn, that is mass of nucleons of parent nucleus, that is X, minus mass of nucleons of daughter nucleus Y, minus Me, mass of electron, multiplied by C square. This shows energy released from mass difference of parent and daughter nuclei minus the electron mass. Mn here is mass of nucleons and Me is the mass of electron. After some modifications, equation become Q1 equal to mass of nucleons of parent nucleus X plus Zme, that is the mass of all electrons present in parent nucleus, parent atom, minus mass of nucleons of daughter nucleus, that is Mn multiplied Mn of Y, minus Z plus 1 Me. Okay, that is the number of electrons present in the daughter atom, that is Z plus 1, multiplied by C square. For beta plus decay, Q2 involves similar mass differences but includes positron mass. So Q1 equal to, now this M is the mass of the atom of parent atom, okay, and minus mass of daughter atom. Okay, why we are considering now mass of the whole atom? Because we have added the mass of electrons in the mass of nucleons. Okay, addition of mass of nucleons and mass of electrons in above step results in mass of entire atom. Now equation is Q2 equal to capital Mx, that is the mass of parent atom, minus My, that is mass of daughter atom, multiplied by C square. This accounts for the mass difference between parent and daughter nuclei multiplied by C squared. Now let us see why other options are incorrect. So option B states that Q value for both beta minus decay and beta plus decay is capital Mx minus capital My C square. Okay, so let's see why option B is incorrect. So in beta minus decay, Q1 is equal to Mx minus My C square. For beta plus decay, Q2 came out to be Mx minus My minus 2Me C square. So Q value differs by minus 2Me for beta plus decay due to positron and electron mass. Okay, hence option B is wrong. The correct Q value for beta positive decay is Mx minus Mv minus 2Me C square, not Mx minus Mv C square. Option C states that Q value for beta minus decay is Mx minus My minus 2Me square, and for beta positive decay is Mx minus My plus 2Me C square. Let's see why option C is incorrect. So this is incorrect because for beta minus decay, the correct Q value is Mx minus My C square, as there is no need to account for the mass of electrons. Additionally, the term 2Me in the Q value of beta positive decay is incorrect. It should be minus 2Me, not positive 2Me. So in beta minus decay, Q1 equal to Mx minus My C square. And in beta positive decay, Q2 is equal to Mx minus My minus 2Me C square. So option D states that Q value for beta minus decay is Mx minus My plus 2Me C square, and for beta positive decay Mx minus My plus 2Me C square. Let's see why this option is incorrect. So in beta minus decay, a neutron turns into a proton, emitting an electron and antineutrino. The Q value is Mx minus My C square. For beta positive decay, a proton turns into a neutron, emitting a positron and neutrino. The Q value is Mx minus My minus 2Me C square. The given options incorrectly add plus 2Me for both. So for beta positive decay, the correct value is Mx minus My minus 2Me C square, not Mx minus My plus 2Me C square. Now Next exemplar 13.5. Tritium is a isotope of hydrogen whose nucleus triton contains 2 neutrons and 1 proton. Free neutrons decay into protons plus electron plus antineutrino. So in question it is asked that if one of the neutron in triton decays, it would transform into helium-3 nucleus. And this does not happen. Why? So 4 options are given and you have to choose the correct one. So A, triton energy is less than that of helium-3 nucleus. The electron created in the beta decay process cannot remain in the nucleus. Both the neutrons in triton have to decay simultaneously, resulting in a nucleus with 3 protons, which is not a helium-3 nucleus. Free neutrons decay due to external perturbations, which is absent in triton nucleus. So option A is the correct option. Let's see the solution in detail. So isotopes of an elements are having same atomic numbers and different mass numbers. Let's see the solution in detail. So in tritium, 1 proton and 2 neutrons are present. So free neutron decays into a proton, electron and antineutrino. If 1 neutron in tritium decayed, it would form a helium-3 nucleus, 2 protons, 1 neutron. But this doesn't happen due to nuclear stability. The decay is prevented by the strong nuclear force holding the nucleus together. So transformation of a tritium nucleus into helium-3 nucleus through the decay of one of its neutrons would require the final state helium-3 to have a lower energy than the initial state tritium atom. In tritium, a neutron decays into a proton, electron and antineutrino. This would turn it into helium-3 nucleus. But this doesn't happen because tritium is more stable than helium-3, meaning its energy is lower than that of helium-3 nucleus. So tritium is more stable than helium-3 nucleus. So the decay doesn't happen. Energy-wise, tritium has lower energy, making the transformation unfavorable and cannot occur spontaneously. Now let's see why other options are incorrect. So option B states that condition given in the question is not possible because electron created in the beta decay process cannot remain in the nucleus. But this is incorrect because the electron produced in beta decay is not required to remain in the nucleus. It is because the emitted electron during decay would leave the nucleus and does not prevent the transformation. Option C states that both the neutrons in triton have to decay simultaneously, resulting in a nucleus with 3 protons, which is not a helium-3 nucleus. This is incorrect because the decay of a single neutron in triton would result in helium-3 nucleus. The decay of 1 neutron is enough to form helium-3, so both neutrons don't need to decay. Option D states that free neutrons decay due to external disturbances, which is absent in triton nucleus, and this is incorrect because free neutrons decay spontaneously due to the weak nuclear force, not due to external disturbances. Absence of external disturbances in the triton nucleus does not prevent the decay of a neutron within it. Next, question exemplar 13.6. Question asks about the fact that why heavy stable nuclei have more neutrons than protons. So 4 options are given, you have to choose the correct one. So option B is correct. In heavy nuclei, more neutrons than protons are needed to counteract repulsive electrostatic forces between protons, which may reduce the stability of nucleus. Neutrons are neutral particles that do not contribute to electrostatic repulsion. They contribute to the strong nuclear force which binds the nucleus together more effectively, especially in heavy nuclei, without adding to the repulsive electrostatic interactions, making them essential for the stability of heavy nuclei. Now let's see why other options are incorrect. So option A states that the reason of stability of heavy nucleus is that neutrons are heavier than protons. Mass difference between neutrons and protons is not the reason for the neutron to proton ratio in stable heavy nuclei. In heavy stable nuclei, more neutrons than protons are needed to counteract repulsive protons. Therefore, stability is more influenced by the balance between nuclear forces and electrostatic repulsion. So option C states that neutrons decay into protons through beta decay. While neutrons can decay into protons, this process does not explain why stable heavy nuclei have more neutrons. Beta decay is more relevant to the stability of individual neutrons rather than overall neutron to proton ratio in heavy nuclei. Beta decay converts neutrons to protons, but this doesn't explain the neutron excess in stable heavy nuclei. Option D states that nuclear forces between neutrons are weaker than between the protons, but this is incorrect because nuclear forces are actually similar in strength between any nucleons. Nuclear forces doesn't depend upon charge of nucleons. Difference in stability is due to the repulsive electrostatic forces between protons, not the strength of nuclear forces. Next example 13.7. In a nuclear reactor, moderators slow down the neutrons which come out in a fission process. Question is that why the moderator used have light nuclei and heavy nuclei will not serve the purposes. 4 options are given and you have to choose the correct one. So option B is the correct option. So thinking process for this question is when there is an elastic collision between two bodies of same masses, their velocities are exchanged. So according to the question, the moderator used have light nuclei like proton. In a nuclear reactor, light nuclei like protons slow down neutrons via elastic collisions. In a nuclear reactor, moderators slow down neutrons using light nuclei like protons. In elastic collisions, neutrons transfer all their energy to lighter nuclei and their velocities get exchanged. That is, neutrons come to rest and protons move with velocities of neutrons. Heavy nuclei don't work because they don't exchange velocities effectively. Heavy nuclei don't slow neutrons effectively and will not serve the purpose. Now let's see why other options are incorrect. So option A is incorrect because heavy nuclei will not break up easily under neutron collisions. They are generally stable and can withstand such interactions. In a nuclear reactor, light nuclei slow neutrons via elastic collisions, exchanging velocities. Heavy nuclei can't do this. So option B is correct. So option C is incorrect because net weight of the reactor is not a primary concern in the choice of moderator. The effectiveness in slowing down neutrons is the critical factor. Option D is incorrect because substances with heavy nuclei can exist in solid state at room temperature and the state of matter is not a determining factor for their use as moderators. Next question is multiple choice question and more than one option can be correct. The given question focuses on the challenges associated with nuclear fusion, specifically the process of combining two deuterium nuclei to form a helium nucleus. It presents a multiple choice question that explores the reason why such fusion processes are not feasible under normal conditions, that is at ordinary temperatures and pressures. Question asks about the reason for that infeasibility of fusion process under normal conditions. 4 options are given and you have to choose the correct ones. More than one option can be correct. So options are nuclear forces have short range, nuclei are positively charged, The original nuclei must be completely ionized before fusion can take place. The original nuclei must first break up before combining with each other. So both option A and B are correct options. Fusion needs high temperature pressure to overcome electrostatic repulsions between the nuclei of two atoms. At ordinary conditions, particles don't have enough energy to fuse. Nuclei are positively charged, so they repel. Nuclear forces are short range and only act at very short distances, around 10 to the power minus 15 meters. So nuclear forces can't contribute in fusion process. Now let us see why other options are incorrect. So option C is incorrect because the original nuclei do not need to be completely ionized before fusion can take place. Fusion can occur with nuclei that are already ionized or partially ionized, as long as they have enough kinetic energy to overcome the electrostatic repulsion between the nuclei. Option D is incorrect because the original nuclei do not need to break up before combining with each other. Fusion involves the direct combination of nuclei, not their or disintegration. So this is all about NCERT Exemplar of chapter Nuclei. I hope you understood it well. Thank you.